In this lecture, we shall look at connected components of a undirected graph and introduction to the Fiedler value and Fiedler vector. But first, a brief review. Here's the definition of the Laplacian. We have a weighted undirected graph, and this is the weight matrix. It's symmetric because this is undirected, and so the in degrees and out degrees are the same of each vertex. We have 6 vertices here, A, B, C, D, E, and F. Call them 1, 2, 3, 4, 5, and 6. And so the degree matrix is a diagonal matrix consisting of the degrees of the vertices 1 through 6. And the Laplacian L is simply D minus W. So this matrix here is the graph Laplacian. The diagonal elements are all positive because they are the degrees of the vertices, and the non-diagonal elements are 0 or negative because you have a negative weight here. And also note that the sum of all the elements in each row of the Laplacian adds up to 0. So 3.5 minus 1.5 minus 1 minus 1 is 0. And likewise, let's look at the last row. Negative 1 plus 2 equals 0. So formally, this is the Laplacian of a undirected weighted graph. L equals D minus W. Its component in the ith row and jth column, Lij, is when I is not equal to j for the off-diagonal elements, it's negative of the weight between vertices I and j. And when I equals j, that is a diagonal element, then it's equal to di, the degree of vertex I. The eigenvalues of L, it turns out, are real and non-negative. The smallest eigenvalue is lambda 1. So the eigenvalues are sorted in ascending order. And the smallest eigenvalue is 0. Lambda 1 equals 0. The sum of squares theorem. So this theorem states that x transpose Lx equals half of this double summation over indices of vertices I and j of wij xi minus xj squared. This n here is the cardinality of the set of vertices. This is an example. So I have this graph here, and I've called these vertices A, B, C, D. Their indices are 1, 2, 3, and 4. And so I assign values to each vertex, 1, 2, 3, and 4. x1 through x4 are the values. I arrange them in a n by 1, which is a 4 by 1 vector, and so x transpose Lx evaluates to this 64.5. It follows directly from the sum of squares theorem that the Laplacian is symmetric, positive, semi-definite. L is greater than or equal to 0. Whence, the eigenvalues of the Laplacian are real and non-negative. Lambda I is greater than or equal to 0, where I equals 1 through n. N is the total number of vertices. The smallest eigenvalue of L and its eigenvector are lambda 1 equals 0, so it has a 0 eigenvalue. The Laplacian is singular, and the corresponding eigenvector is 1 over square root of n of this vector of all ones. So now we begin with connected components of a graph. So here's an example of a graph which contains 6 vertices A, B until F. Clearly, this graph can be divided into 2 separate subgraphs. One subgraph containing vertices B, C, and D, and the other subgraph containing the vertices A, E, and F. So these are called the connected components of the graph. This graph with 6 vertices has 2 connected components. For our purpose, we shall assume that a connected component is merely the subset of the set of vertices. So BCD is one connected component, A, E, and F is the other connected. But in reality, if you want to define each connected component in terms of a subgraph, then you need to also consider the relevant set of edges and the corresponding weights. Now, between B and D, there is no direct edge, but you can clearly see that there's a path connecting B with D. That path goes through C. So, between any pair of vertices within a connected component, there always has to exist a path between the vertices. On the other hand, there is no path from A to C or from B to F. Why is that? That's because there are no edges between vertex in one connected component with any other connected component. So this is the formal definition of a connected component. In our example, we had 2 connected components. Let's call them C1 and C2. There is a path between every pair of vertices within a connected component, and there is no path between a vertex in a connected component to any other vertex that's in V minus C, that's outside the connected component. So these are the 2 criteria that make up a connected component of a graph. So now let's look at the Laplacian of this graph. This is the Laplacian. The vertices A, B until F have indices 1 for A, 2 for B, 3 for C, and so forth. And these are the weights of the graph which appear at the corresponding positions in the Laplacian. So let's take this edge between B and C. It has a weight of 2.5. This is index 2 and C is indexed 3. So at the row 2 and column 3, we have negative 2.5, which again is negative 2.5 here at row 3 and column 2, which correspond to B and C. So let's focus on the connected component shown here. And so we retain columns and rows 2, 3, and 4 of the Laplacian and discard the rest. This yields this smaller 3 by 3 matrix here, this matrix, which is in fact the Laplacian of this connected component BCD. Likewise, let's turn our attention to the other connected component consisting of vertices A, E, and F. So now let's look at rows and columns 1, 5, and 6. 1, 5, and 6, and ignore the rest. So this 3 by 3 matrix now turns out to be the Laplacian of this subgraph or connected component AEF. The remaining elements of the Laplacian are filled with all zeros, and that's because there is no edge connecting a vertex from one component, connected component, to the other connected component. So we have all these shaded blocks, which are zero blocks. Now let's look at the eigenvalues and eigenvectors of this Laplacian. We know that if we multiply the Laplacian with a vector of all ones, we get zeros, which is 0 times this vector of all ones, which by definition makes this vector of all ones a eigenvector of this Laplacian. Normalizing it, we get v equals 1 over square root of 6 of this vector of ones, which is an eigenvector corresponding to this zero eigenvalue lambda equals 0. But if we multiply the Laplacian with this vector 0, 1, 1, 1, 0, 0, we again get all zeros. Why is that? That's because I have put ones in the places corresponding to the vertices B, C, and D. And we already saw that this 3 by 3 matrix was the Laplacian of this smaller graph. Everywhere else in this vector, you have zeros. So effectively, we are multiplying this Laplacian with this 1, 1, 1, which naturally will give us all zeros. Whence v equals 1 over square root of 3. I've just normalized this vector here, 0, 1, 1, 0, 0. This here is also another eigenvector corresponding to the same lambda equals 0. In exactly the same manner, when I multiply the Laplacian with this vector here, where the ones correspond to the vertices A, E, and F, I'll again get all zeros. So I normalize this vector and I get v equals 1 over square root of 3 of 1, 0, 0, 1, 1, which is yet another eigenvector of the same eigenvalue lambda equals 0. Hence, this v is yet one more eigenvector for the same lambda equals 0. And so is this v. In fact, we can make up any number of such eigenvectors for lambda equals 0. However, all these eigenvectors are not linearly independent. The general form of any eigenvector of lambda equals 0 is of this form, where A and B are two scalar quantities. To get the generic expression for an eigenvector, I put A's at the places corresponding to the connected components A, E, and F, and B's at the places that are associated with the other vertices B, C, and D. Now, they were not all linearly independent. So what we can do is we can assign two different pairs of values to A and B, maybe 1, 0 and 0, 1. And so we get two linearly independent eigenvectors. Since we have two parameters A and B, we can only get two independent eigenvectors. Therefore, we see that the multiplicity of lambda equals 0 is 2. In general, the multiplicity of lambda equals 0 is equal to the number of connected components. It was 2 in this case because this graph had 2 connected components. That we shall see is how to relabel vertices in a meaningful manner. So after relabeling, I get this new graph, and its Laplacian is this. What have I accomplished? This Laplacian is nothing but the same as the previous one, where the rows and the columns have been rearranged, and I see that this arrangement produces a block diagonal Laplacian. So how did I do the rearrangement? Vertex A remains vertex A. So if you look here, A is still A. B becomes D. B becomes D. C becomes E, and C becomes E here. And in terms of the indices of the vertices, 1 is still 1, 2 becomes 4, 3 becomes 5, and so on. So I get this permutation matrix. I have 1 in the first place. So in the first row, I have 1 in the first column. I have 4 in the second place. So in the second column, in the second row, I have a 1 in the fourth column. I have 5 in the third place. So in the third row, I have 5 in the fifth column, and so on. And so I get this permutation matrix. So this is the old Laplacian, and we make this transformation using this permutation matrix that we just saw. Pre-multiplication rearranges the rows of L, and post-multiplication with P transpose rearranges the columns of L. And so we get this transformed Laplacian of this graph, and it has neatly divided the matrix into diagonal blocks. L1 is the Laplacian of connected component C1, and L2 is the Laplacian of the connected component C2. So this brings us to an important theorem, the connected components theorem. So the algebraic multiplicity of eigenvalue lambda equals 0 of the Laplacian is the number of connected components of the graph. It's an important theorem. Proof. Suppose K is the number of connected components in the graph. Therefore, there exists a permutation matrix P such that PLP transpose is this block diagonal matrix. L is the Laplacian of this graph, and P is our permutation matrix, and L1, L2 until Lk are the smaller Laplacians of the connected components. The potential eigenvectors of this transformed Laplacian will be 1, 0, 0, 0, 0, 1, 0, 0, all of these. As a side note, note that these 1s and 0s are block vectors, but they are not of the same sizes. So their sizes would depend on the cardinality of the connected components. Now, there are only k linearly independent eigenvectors of the transformed Laplacian PLP transpose for lambda equals 0. This is the general expression for these eigenvectors. Alpha 1 through alpha k are scalar coefficients, and C1, C2 until Ck are the connected components. Now, since PLP transpose and L are similar matrices. They have identical eigenvalues and their eigenvectors follow this relationship. If V is an eigenvector of this transformed Laplacian, then P transpose V is the eigenvector of the original Laplacian. Hence proved. There's an alternate proof for the same theorem, which is based on the sum of squares theorem. It's a little lengthier, but more convincing too. So here we have two summations. The first summation is over index I, and the second summation is over index j. Of course, both summations are being carried out over all vertices in the graph. What I've done is I've taken the first summation, outer summation over I, and then divided into two separate summations. This summation is over all connected components, and then the second summation here is all vertices within that connected component Ck. Now, let's focus on the second summation here, which is this. It's over index j. I split it into two parts. One part is over all vertices in Ck, and the other summation is over all vertices outside of Ck. So this is where we are. Now, look at this index and this index here. This summation is over all i's, all vertices in Ck, in the connected component Ck. And this summation is carried out over all vertices j that are outside of this connected component Ck. So clearly, there is no edge connecting I and j together because they're in different connected components, whence the weight wij will be equal to 0. And this will be true for all the weights in the second term. So the second term completely vanishes. Whence this is what we are left with. Here in the second summation and the third summation here, both are being carried out over vertices in the same connected component. So this can be expressed in another manner. This is the first summation over all connected components. This summation here is over all pairs of vertices lying within the same connected component Ck. Ek can be defined in this manner. Ek is the set of all pairs of connected components, vertices in the connected component such that ij is an edge. And now, how do we make this equal to 0? For every connected component Ck, we assign the same values to all its vertices. So xi equals xj as long as I and j belong to the same connected component. But if I and j are in different connected components, they need not have the same value. So as long as within each component xi equals aj, this entire summation, double summation, vanishes. So this first, obviously, the first for every connected component Ck, if we assign xi equals xj, this becomes 0, whence the entire x transpose Lx becomes equal to 0. Now, we invoke Rayleigh's theorem. What Rayleigh's theorem says is that 0 is an eigenvector and x is an eigenvalue, but of course we have to normalize x. Why is this an eigenvector? Because L is positive semi-definite, so x transpose Lx cannot acquire negative values, so the minimum of x transpose Lx must be equal to 0. All we are left to do is normalize what we have so that we get a normal unit eigenvector. So lambda equals 0 and V belongs to the spectrum of the Laplacian L. Hence proved. The next topic is Fiedler value. We'll just have a brief exposure to what Fiedler value is. Fiedler value. Let's restrict for a moment our attention to fully connected graphs. The Fiedler value is the smallest non-zero eigenvalue lambda 2 of the Laplacian. The corresponding eigenvector V2 is called the Fiedler vector. Now, if the graph were not fully connected, then obviously lambda 2 would have been 0. If the graph had 3 connected components, even lambda 3 would have been 0. But we are restricting our attention to fully connected graphs. In such fully connected graphs, higher Fiedler value implies more connectivity. I shall illustrate this with an example. Lemma. The sum of all elements of the Fiedler vector add up to 0. 1 transpose V2 equals 0. Why is that? Well, we know that V1 transpose V2 equals 0 because L is a symmetric matrix. And we also know that V1, if you don't normalize, is equal to a vector of all ones. This one vector. And so from these two, we can directly arrive at the statement of this lemma. Fiedler value. So we have a graph and the Fiedler value is lambda 2. Lambda 1 is always 0. Now, if k is the number of connected components of the graph, if k is greater than 1, then obviously the graph is not fully connected, in which case lambda 2 is equal to 0. When k equals 1, then lambda 2 is greater than 0, strictly greater than 0. But the value of lambda 2 tells us how well connected the graph is. If G has more edges or higher weights, then lambda 2 will be more. Here's an example. This is not a fully connected graph. What's its Fiedler value? Its Fiedler value is 0. Now I insert a new edge to this graph joining A and D. And I make appropriate changes to the Laplacian. The Fiedler value changes to 0.45 because this is no longer a graph with two different connected components. It's a fully connected graph now. Next, I insert yet another edge, so it becomes more fully connected. Or rather, its connectivity increases. What happens to the Fiedler value? The Fiedler value has increased to 0.56.